Okay, any questions on the homework set 2 problems?
Do we need to, how do we get
Which problem?
from 4.9 and on?
Okay.
How do we get a beam weight? Do we need to get a beam weight, or is it?
Yes. One of the things we discuss engineers do that we don't do in science is trial and error. Where we do less in science. So you make a reasonable guess, and then if at the end your guess was way off, you redo it. So you assume a reasonable size, reasonable unit weight, weight per unit length, 500 pounds per foot, 1,000 pounds per foot, and then you analyze, you find the size. If the values are close, you say that's good enough. If, let's say, your beam is 20 by 40, you assume it's 10 by 10. It's way too small. You have much more weight that you did not consider. You design and then you go back based on this cross section, redo it. But if your values are close, and a little, particularly if you overestimate it, then you are good.
How many solutions do you want us to find?
2, 3, let's say. Of course, solutions are as easy as just plugging numbers and getting a pairs, right? Getting pairs. Any other questions?
What do you mean solutions you want to?
Let's say at the end you get BD squared. Oh, that reminds me of a correction. I'll let you know. One of you told me I have to correct what I said last time. But let's say your BD squared is equal to 2,000. There are lots of B's and D's that give you 2,000. So you choose a few B's and you find corresponding D's. You say if B is so much, D is this much. If
So then once you determine, once you figure out the rebar size,
this is before rebar size. Yes.
Once you figure out the rebar size, and
You mean after this step?
after the
Okay.
steps, you determine, and you compare the original MU with like the safety factor with MN.
I need to be able to follow the question more closely.
My question is, how do you, if your original MU, the original ultimate moment, is like, it's going to be, say it's less than the AS we determined based on.
MU cannot be less than AS. I mean,
less
make
than
this,
the
okay.
reduced factor of,
Let's make that statement one more time. Okay, let's start all over. One more time.
okay, so the original ultimate moment.
Okay, MU.
Safety reduction factor of nominal moment.
Nominal. So I mean, those terms should be very specific. So is less than phi mn, which should be, because that's the way you design. In other words, what you do is you set them equal and you calculate the way this is equal.
So
Okay.
My question is, now, if MU is less than this nominal moment,
MU can, I mean, you set them equal. It will not be less, it will be equal. You set it equal and you find B and D. So therefore it's going to be equal because you chose B and D to be equal. One thing you might be thinking is your B and D, you round them up. Is that what you are thinking?
so I'm talking about after we find BD squared and we determine.
Let's just do this one. Let's say this is 4,000. Let's say this is 4,000. We say if, let's say B is 12. Can you calculate D? Divide 4,000 by 12 and then take the root of it. Let's just finish this one and then we get to the next question. 18.25. If B is equal to 14, D is equal to 16.9. 90. And if B is equal to 16, D is equal to,
25,
no, it should be less.
15.8.
15.81. So if you use these pairs, either of those two pairs, your mu is equal to phi mn because you set them to be equal. Okay?
I understand that part. So that
Okay.
when we determine a reasonable base and height and cross section,
Reasonable, you mean rounding them? Or no? What's reasonable?
I don't round.
Okay, what's reasonable then? So you just add 3 inches to D. Now it exactly still is correct.
One that will give me of what I assumed the beam weight was.
You are talking about now beam weight.
Yes.
Okay, so that has nothing to do with these things then. It was, your question is this: if my beam weight is not exactly correct, what do I do with it?
It's not, I'm trying to.
No? Okay. So let me ask you this. Let's say beam weight was given to you,
Okay.
or beam weight was included in the weights that were given to you.
Yes.
In that case, what is your question?
So then, once we solve for the cross section, and we
Means what? Solve for B and D, which are these numbers.
when we figure out what B and H is,
Okay, which are those numbers? Yes.
and then we now we're gonna figure out which rebar.
Okay, so you have AS. You have AS. From AS, you find bar numbers.
So you want on either.
The bar numbers to be more or equal, correct?
So then once we determine the AS and we find the nominal moment.
If you are doing more rebars, your nominal moment is going to be phi mn. So let's say you choose this one, and we say AS provided is larger than AS required. So that means, for instance, your AS required is 2.8 inches squared, and you say, I want to use 3 number 9, which is equal to 3 inches squared. So when your AS provided is more than AS required, then you are over designing and you are still satisfying the fact that mu is less than equal phi mn. You set them equal, and then when you make the decision at the end, you overestimate, you don't underestimate. You cannot say, I have 2.8, I provide 3 number 8 that is less than 2.8. As long as you choose more, then you say, I'm satisfying the requirements that mu is less than equal phi mn. There is no additional step needed. This is the requirement. What you start with, you set mu equal phi mn equal, not less than equal. You calculate everything, and at the end, when you calculate AS, in fact, there is another step. We round these things up. I'll talk about that today. Let's say you are not rounding them, you're just calculating your AS, and your AS provided is more. You don't need to go back. It's a good idea to check your MN just for the sake of verification, but your MN, phi MN is going to be larger than MU, and your design is complete. You do not need to redo anything.
Which earlier you said that they should be relatively close. The new.
Relatively close, you are making that decision here. It's your job to decide to how close is close. Is 3 number 9 close to 2.8? No, 3 to 2.8? Give me a better choice. You don't like it? Give me a better choice. It's not a good idea. Sometimes some engineers may think it would be easier, for instance, I choose 2, of course in this case let me make it 2.75. In order to make it even closer, you can say 2 number 9 plus 1 number 8. Just to make them closer. That's, again, from a scientific point of view, is a better solution. From a practical point of view, it's not. Because it's more complicated by several factors. One, number 8 and number 9 are close. People can make mistakes. They pick number 8, they think that it's number 9. So you are increasing the likelihood of construction errors. And you are making drawing more complicated, and they need to think more. Let me rephrase what I said. Do not worry too much about your area being slightly or somewhat more than the area required. We'll talk about it later on as to if you have, let's say, 2.75, considering other requirements, not what we have talked about so far, but other requirements, how we choose the bars. There are other things to satisfy. At this time, just choose, I mean, this is the short story, just choose something that is reasonably close and somewhat larger than 2.75. Now continue if I haven't answered your question yet.
So you've answered most of it. It makes sense. But like, what indicator will we know we need to go change something? As far as like,
If the weight was not approximated, there is nothing to check.
okay.
Here,
But if it was approximated?
yeah, that's a different story. I'll explain that. But if your solution is exact,
Yeah.
your numbers are exact, there is nothing to check. Nonetheless, it's always a good idea, after you did this, after you found the rebars, calculate MN one more time just for verification, just to make sure that you didn't make any mistakes or anything. You're just checking your calculation. Is it needed? No, it's not needed. It's an additional step to make sure that things are correct. If, however, your weight was not exact or you rounded those numbers, I'll explain that today. So what was your question?
My question was, do we need to find several solutions for B and D or also for AS?
Several solutions for B and D. Let me see how your solutions to your problems are. B and D. So identify several solutions, choose one and move forward with one.
Okay.
Other questions? Yes.
Does that mean we're just choosing one B and D and then?
Yes. Correct. You say, for instance, B and D in the past, somewhere, let's say 15 years ago or more, people were thinking about what are a good values or ratios between B and D. Let me ask you this. If you have a choice between I'm trying to come up with two numbers that close. I exaggerate a little bit. 10 by 40 and 20 by 20. A beam is 20 inches wide, 20 inches deep, or 10 inches wide, 40 inches deep. They have the same area. Which one would you choose? And the reason? Why do you think that's easier?
It might just fit the dimensions of the span better.
It could, but 10 by 540 could also fit. So, from a purely mechanical point of view, no other measures, no is easier, is less expensive, or anything else. From a mechanical point of view, which one is a better choice?
The 20 by 20,
The reason? Just mechanical point of view, don't forget.
because you'll have more concrete compared to enough space for rebar, creating a larger compression versus tension zone.
You said two reasons at the end. One was what did you say about rebars?
You'll have less space for rebar in comparison to the amount of concrete.
Less space in which case?
If you had the 40 by 10, you'd have less space for rebar.
So one option is 10 by 40. Let me give you maybe another pair that would be not too drastically different. Let me get 20 by 20. Then this would be, because what is really important is not B times H, is B times D. Okay, so let's say 20, let me make it 23 to be easier. 23, so this would be 20, is 400, and then let's say 18 by, can you find 400 divided by 18? 22.2. So let's say, forget about rounding and everything. We have a section 20 by 20, 20 by 23 that gives, this becomes, let me rewrite this. Forget about rounding again at this time. Let's say this is 25.2. I have 20 by 23 that gives me 20 by 20 B and D, or 18 by 25.2 that gives me 18 by 22.2 that both have the same BD. Okay? Which one is a better choice? Left, right?
I'm not sure.
What does it mean, better choice, from a mechanical point of view?
You want concrete to crush before you go.
That's one measure we will satisfy for both of them.
Option on the right is better mechanical.
Wha-
Better,
Reason?
greater moment of inertia in the bending direction.
Greater moment of inertia at one level is correct. Moment of inertia is important as far as deflections go. When we are designing, we don't design for deflection. That's indirectly correct, but when you design, you don't design for deflection. You design for forces. And when we calculated forces, we didn't use moment of inertia. Remember, why didn't we use moment of inertia? Because material properties at the ultimate level is nonlinear. You cannot use moment of inertia. Your answer is correct at a different level, but what is the more specific answer here? Linked to what you said.
You have more area for compressive force.
Why do you think you have more area for compressive force?
Would you have more area on top of the rebar?
Because more area for which case?
Or positive moment
For the right case or left case?
for the right?
For you are saying the right case is better because
You have more room for the compressive force, like the area of the compressive force.
indirectly again correct. The most important thing is this. Moment is force times R. A section that has larger R is always better. So if you have a choice, to make the beams deeper, mechanically is always better. Because you are making better use of your material. For instance, let me ask you this. How many of you have taken steel structures? Some of you, okay? When you make a steel section, do you use this geometry or this geometry? Why? Same reason. You want more material farther away, as far as you can. The same concept is here. What you want is the distance between the tension and tensile and compressive forces as large as possible. So the larger it becomes, the more economically, you are more economically designing. With a big condition from a mechanical point of view only. In the past, if you look at older books, maybe even some of the newer books, they say that a good D over B is in the range of 1.5 to 2. A good D over B is in the range of 1.5 to 2. That means D, for instance, is twice B, or 1.5 times B. That statement is correct from a mechanical point of view because of the reason we said. You make the beam deeper. However, from actual cost point of view, the left one could potentially be more economical than the right one. When it comes to the actual cost, you need to consider many other factors. The most important factor is the formwork cost, which, I mean, that's not part of this course and is not that we will discuss. But there are some other guidelines as to what is the best dimensions that would minimize the cost of the formwork. The cost of formwork could be as large as concrete and rebar together. Okay, so for instance, I just give you one guideline. Your beam is better to be not narrower than your column. When you make beams narrow and deep, what you end up, your beams become narrower than the column. The column goes up. The column goes up, and then the beam, let me show you here. The column goes up maybe from this direction. The column is going up, the beam is going to be narrower than the column. When the beam is narrower than the column, making the formwork around that joint is very complex. That takes a lot of effort to make it, which has nothing to do with these types of discussion that we have. It's simply how things work at a more complete version. So I'm just giving you one piece that has it's just one item that could be used in design. I don't suggest that you want to do that at this point. But if you want to optimize the design, this old idea that D compared to B should be 1.5 to 2 doesn't hold anymore. There are lots of other things that you can consider that would considerably reduce the cost. Let me give you maybe one more example just to make the point. I have this friend who designs in New York. He said in New York, I'm not sure how accurate or how other factors are involved. I was saying that when you make at a construction site, you usually spend somewhere around $300,000 per day. The workers come, at the beginning of the day they leave, you have spent $300,000. Okay. He was saying that one day we had asked the rebars to come in, and the rebars were cut incorrectly. They had asked the rebars to be cut, they were cut incorrectly. He said we lost 4 hours. 4 hours means $150K. Imagine how much rebars we saved and how much we lost. Okay. He was saying that after that, when I asked someone to design, I say do not cut the bars unless it's absolutely needed. you don't need the rebar, just continue it. You don't need it, but it's less costly. That means make the construction as easy as possible. Overall, you gain. That's the requirement in the US because workmanship is expensive. If you go to another country, materials is more expensive, you may have other requirements. So to cut this long story short, having final product being economically designed is much more than just looking at mechanical characteristics, which requires experience, requires lots of other factors. So, at this time, if I wanted to choose one of these and I don't have any other requirement, I perhaps would go with the first one with the same logic I mentioned that is not really correct, but is a reasonable point to make at this time that a D over B that is about 1.5 is better than the other numbers that are less than 1.5. I could even say that given this, I want to choose another one, maybe 10 may be too small, but let's say if I wanted to choose, I would choose this one based on mechanical characteristics. Yet, I do know that practically is not the best choice. Does that make sense? Okay, so we've just worked within the constraints that we have, within the knowledge that we have, and that. So you choose one, and then you chose that one, you move forward with that one, and calculate your AS. Other questions? So I don't hear any questions on the last problem. Anyone did the last problem?
Well, I didn't do it, I have a question on it, so.
Sure.
The question itself is somewhat confusing, so when you have this beam that's not symmetric, and I understand there's a negative.
When you say the beam is not symmetric, you have to be more specific. What does it mean, not symmetric? The beam itself is not symmetric, or the cross section is not symmetric?
The supports.
Okay, the beam itself is not symmetric. Let me see what the geometry is.
So a certain section.
Which problem was 4.23? Yes. Okay?
So I understand that we're going to have a negative moment and a positive moment between each section.
Try to make the statements more specific. Use the term moment diagram.
Well, at the when we use statics,
When you use a static draw moment diagram, what would happen?
we're going to have a positive moment and a negative moment.
That's correct.
So are we going to analyze each section differently?
When say each section, how many sections do we have?
That's where I need clarification. So
If I ask you how many sections does this beam have, what would you say?
the areas is confusing.
Understand?
Cross-section.
This beam has infinite sections. You can cut every point 0.001 inch is a section. You can cut every point 0.0000001 inch. You have 10 billion sections. When you design a beam, what is of interest is usually the maximum moments. Maximum positive moment and maximum negative moment. Do we put rebars only at the location of the maximum positive and negative moment, or everywhere? Everywhere. What do we do with other sections? We will discuss that later on as to after you design the critical sections, what do you do for sections between the critical sections? So what does that mean? We do not design every section. We design some sections and then we decide later what to do for sections between those sections that we designed. In general, you design a beam for 3 sections: beam ends and close to midspan. That's in general, doesn't hold all the time. In general, you design a beam at beam ends and the center line. In this case, you design for maximum positive moment and maximum negative moment. So let me first see how specifically the question reads here. Live load is placed. So, I mean, it explicitly tells you what to do. It says, select beam size for the largest moment, positive or negative, and then select the steel requirements for maximum positive and negative moment. Finally, sketch the beam and show approximate bar locations.
So once we determine the cross-section, do we treat them as 2 different,
There are 2 different locations.
treat them 2 different cross-sections, basically?
They're not,
They'll have the same cross-section, but.
that's correct. That is,
They might have different.
they will have different rebars.
Locations, but they might have different.
I mean, if they are at different locations, why they should be the same bars? If one is top, one is bottom,
If the moments are equal.
if the moments are equal, you may end up there is no requirement to have any link between what the top bars are and what the bottom bars are. So, therefore, you would design for positive moment and negative moment. And so, what's the next part of the question, if any?
Finally sketch the beam and show the approximation bar location.
What's the question?
No, you answer.
Okay. Any other questions? How many of you had looked at this problem before? You have any questions? Is clear?
Yeah.
Is clear? Anyone else who has looked at the question?
At first, I was confused about how to find the role for the 2 different, for the positive and negative moments, but I'm assuming you just used the diagram that you gave us in the handout for...
They are practically independent. You are designing 2 different sections. As he said, the only dependence is the size of the cross section remains the same. Why do you think the size of cross section would remain the same in practice, based on what we just discussed?
You want level beams.
You can make the beam deeper at the bottom, which at the top would be level. I mean, I really don't care if this beam is going down a little bit here, doesn't concern me. Formwork cost. Imagine you want to change the cross section. That costs a lot compared to just straight. Okay? So the cross section is the same, the amount of rebar is different, and I'll tell you this, you should have more questions. I'll give during the break between 2 lectures, I would suggest you look at it one more time and ask more questions. And please do not send me an email 10 o'clock, I just have one question. If you have questions, you see me or the TA during office hours. Okay, so we are done with two basic things. How to design, how to evaluate an existing beam. A cross section is given to you. The question is, what is M crack? What is M service? What is M ultimate? That's evaluation. We have also seen in this set of homework problems, homework set 2, as to how do we design at least simpler cases. Some information about cross section is given, and then you want to design. What we want to start today is how do we design buildings. Okay, so that's why you see this model is here. As you recall, I defined structural engineering as a profession in which we transfer loads from point A to point B. That's our technical job. How to transfer loads from one point to the other, usually from the point of application to the support. When you transferring the load from the point of application to the support, you need to make sure there is a complete load path and understand the load path. That is, how does the load transfer from the point of application? Let's say we have some load here. This is the roof and the snow comes, and then we want to know what happens to this load. The load will apply to the floor. The load applied to the floor will transfer to the beams. So this is the floor. I applied the load. There are beams, in this case on all four sides. The load will go to the beams. One question would be, which beams will take more load? These two beams or these two beams? That we will discuss today. But the load from the floor goes to the beams. The beams would transfer the load to the columns. The columns would bring down the loads to the footings, and the footing would transfer the load to the ground. That is a complete load path from the point of application to the support, which is the ground. Slab to beam, beam to column, column to footing. Okay. When we apply more load here, would that mean we applied more load to this beam? The answer is no. We are applying the load here, and doesn't mean we are applying to this beam. In other words, if I have a building like this, 2-story or 100-story, same geometry, and I'm looking at gravity loads, the beams for all stories are almost the same. That means the loads from higher floors are not going to transfer to the lower floors, are going to transfer through the columns. It doesn't go to the beams with some approximation. So the load that I apply here, the effect of that gravity load on this beam is negligible. That is, if I have 1 story above or 100 story above, doesn't make any difference. As again, we are talking about only gravity load. Don't confuse that statement with lateral loads. Lateral loads is different. For gravity loads, when I have this, let's say this beam is 20 by 20, if you are designing only for gravity, if it's 2 stories, 20 by 20, if it's 100 stories, still is 20 by 20. Those stories would not affect the beams. However, if you have 2 story or 100 stories, your columns would be very different, because columns are collecting the loads from beams, and as you go down in the columns, they have more and more and more force. Not the beams. Under gravity load, not the beams. So you must, I have seen some students, have this misunderstanding that if it's taller, the load of those beams would transfer to this beam. The answer is no, it will not transfer to the beam. It would transfer to the column. Why? Due to the load path. Load path is from the, under gravity load, from the slab to the beams, from beams to the columns, from the columns to the footing. This is called a complete load path. You need to understand the load path in order to model your structure. As I mentioned last time, structural modeling is the most technical part of structural engineering. In order to model the structure, you need to know how the loads are transferred. I apply load here, the slab would deform. Depending on the shape of the slab, which we'll talk maybe later today, loads would transfer, we will see later on, that would transfer more to these longer beams, not to the shorter beams. Therefore, in this case, in this building that you see here, or in this model, the load applied here will go more to these beams than to these beams. From these beams, we'll go to these columns in this direction and then go down to the footing. Based on the way the load is transferred, we'll do different types of modeling. Our goal in this class is finally at the end, in the final exam, if I give you a building like this, you should be able to design everything. The beams, the floors, the columns, and the footing. The 4 components that you see here, one more time, are the slab, the beams, the columns, and the footing. 4 main components. There are buildings in which they have walls. That's what we are not discussing in this class. Walls are usually meant for lateral loads. Here we are focusing on gravity loads. When we design those elements, we will primarily design for flexure. Flexure would be most of the calculation. There is some, or at least the more important part of calculation, and the parts that would control the design. The design is primarily controlled by flexure. We do the flexural design, and then we do other types of designs. When you look at the floor system, maybe before going to the floor system, remind you one more time on the load path. Whatever you design, you want to design a railing, you want to design a post. Whatever you design, you need to start thinking, where is the load applied and how am I transferring it to the support? That's the most crucial part. You need to make sure everything is done properly. If there is a slight gap somewhere, the structure would fail from that gap. You cannot say the load somehow will transfer. We don't have such a thing, somehow will transfer. Our job is to transfer the load completely. There is no place, absolutely no place you can say, hopefully something would happen here. There is no such a thing. You need to design all the pieces. So having said that, if you think about the floor system, a floor system, why don't we take, because it's late, why don't we take a 5-minute break and then we'll continue with the floor system. Meanwhile, feel free to look at the last homework problem.
Excuse me, I have a sign here.
When would we use this graph instead of using like the roll?
Questions on this asked during the class so that everybody hears.
Oh, okay.
You can just, when we start, just ask.
Sorry, this didn't get all the way around.
Okay. Yes, just 1 second. Yes.
Office hours today.
Today is what, Tuesday? Tuesday,
Yeah.
yes, right after the class.
Okay. I think honestly, it said Monday and Wednesday. So there
The
was-
TA is Monday, Wednesday, I am Tuesday and
Oh,
Thursday.
okay. You have it today. Okay.
If you, I'll remind everybody of the
Okay.
office
Yeah, 'cause I
hours.
was just gonna finish the homework today, and if I had any questions, as I do it.
So I would recommend following what I said, do
Yeah.
this beforehand, it would be
Yeah.
much more effective.
Yeah.
Put into an automated voice message.
standards that you want to work with. So you go.
Exacto. Es muy organizado. Aquí tengo gas. Yo solo escucho excusas en la iglesia. Y hoy estaba. Estas son muy largas. 3 horas es muy larga.
So we were talking about floor systems. There are many types of floor systems. One of them is slab. Slab floor system is simply a constant, usually constant thickness concrete across the floor. For instance, if you look at this sideways, this thickness is constant and is everywhere the same. So this is called a slab. We have another system called joist floor. joist floors, unlike slabs that are constant thickness everywhere, are what we do is we run beams, smaller beams, usually in the longer direction. These are joists. Joist is practically a small beam. So we have these joists, and then because we have the joist, the slab does not need to span from beam to beam. The slab can transfer from joist to joist, which is shorter. Therefore, the slab that would cover everywhere becomes thinner. That is one type of design. For instance, in this case, this is the joist without the slab. Obviously, this cannot be the floor. Floor needs to be covered. So we cover the joist with the slab. If you look at this portion of the slab, you can see that the slab is on top of beams and supported by these joists. So this slab is going to be thinner than this slab. And that sometimes is a more economical design. So these are, for now, two types of floor systems: slab system and joist floor system. There are other types of floor systems as well, but let's just stick to what we discussed so far. The slabs in general are two types: one way or two way. What does it mean, one way or two way? Let's say this is a floor system. I'm showing the plan view. What does it mean, plan view? That means we are looking at the floor from above. That is, in this case, if this is the building, we are looking at this floor from above. And what I'm showing here are beam lines. Those lines, each line would represent a beam. The intersection between beams are columns. Where two beams intersect, this beam and this beam intersect, we have a column. So that means we have columns. I don't show them usually, but I'm showing it for the first time so that you can see. Again, this is the only time I showed you which this detail. Later on, I just show the beam lines. So we have those beam lines that represent the center line of each beam. Just one line at the center of the beam. The columns are there. Therefore, if you want to think about beams, beams are like this. We call these beams longitudinal beams. Usually the beams that we look at them in front, usually on the longer direction, not necessarily longer, but from the front they call longitudinal, and the one that are in the other direction called transverse. These are longitudinal beams. These are transverse beams. Simply they are in the other direction, transverse direction. Again, I'm showing it just once. From now on, I will show only the center line of beams. And you should think about this as a whole. So we have beam center lines, we have columns, and then we have beams if you want to show how wide the beams are. If the load is applied to a floor, this load can be transferred in this direction as well as in this direction. We call this slab a two-way slab. What does it mean, a two-way slab? That means the slab transfers the load in two normal directions. Some of the loads go in the longer direction, some of the load goes in the shorter direction. In general, all slabs are two-way. That means regardless of how long in one direction or short in the other direction, the loads will be transferred to both beams. However, from an engineering point of view, if a lot of load is transferred only in one direction and only a small portion of the load is transferred in the other direction, we call that slab one-way slab. So what is a one-way slab? When a lot of load is transferred in one direction. Then the question is, what would quantify a lot? When is a lot, when is not a lot? The code says if the slab panel dimensions, each one of these is called a panel. So each one of these is a panel. If the panel dimension is such that one is larger than equal twice the other one, if B, which is one dimension, is larger than twice the shorter direction, we call that a slab a one-way slab. So the way you identify a floor system is one-way or two-way is just looking at the dimensions of the slab. If, let's say, one dimension is 15 feet, the other is 20 feet, the ratio is 1.33, that's a two-way slab. That means loads will be transferred in two normal direction. But if in one direction, let's say, is 15 feet, in the other direction is 35 feet. 35 divided by 15 is more than 2. We consider that a one-way slab. That means the load is transferred only in one direction. If this is the case, B is more than 2A, which direction do you think the load is transferred and why? Would it transfer to the longer beams or to the shorter beams, and why? The longer beams.
Yeah.
The reason?
Because the distance between the center of the slab and the extremity of the longitudinal like part of the slab is smaller than the other.
Why that distance is important?
Because that's the distance that the load has to travel.
And then why, when it needs to travel more, it would travel less?
Because it would find the easiest path, the easiest path for travel.
You are on the right track. It needs to become a little bit more technical. So the argument so far is the load will transfer in the shorter direction simply because it's shorter. That's at some level is correct, but not technically complete yet. Any other enhanced version of that answer?
Load follows stiffness. Shorter direction.
That's correct. Shorter direction is
Stiffer.
stiffer. Why the direction that is stiffer would take more load?
Because it has more deflect less.
Would the beam deflect less? Would the slab would deflect less in the transverse direction than in longitudinal direction? So let me just repeat what you said. Your answer was it goes in the shorter direction because shorter direction is stiffer. So we need to explain what that means for now, but in a moment. But let's say we understand that shorter direction is stiffer. Then your logic was the reason for that is the beam in the shorter direction or the slab in the shorter direction would deflect less than the longer direction. However, if you look at the slab, let's say this point, and the middle of a slab, let's say it deflects 1 inch. So that 1 inch is the same in the transverse direction and the same in the longitudinal direction. If I ask you how much did this line deform, the answer is 1 inch. And if I ask you how much did this line deform, the answer again is 1 inch. Therefore, it is not quite that their deflection is different. In fact, that is correct. So the reason the load goes in the stiffer direction more is that their deflections are equal. However, as he said, the shorter beam needs more load to deflect the same amount that the longer beam would deform. If you have a short beam and a long beam and they deform the same amount, the shorter beam must have much more load. Otherwise, it would not deform the same amount. So, which direction does the load go through more? The direction that is stiffer. Why? Because the deflection in two directions are equal, and a stiffer beam would need more load to deflect the same amount. These were qualitative evaluation of what happens. If you want to look at it from a quantitative point of view, think about a beam that has a span of A, or 1B and 1A. A is shorter. And let's say this has Q1 applied to it. This has Q2 applied to it. We know that slab or beam deflection under distributed load is 5Q L to the power of 4 divided by 384 EI. So that's the deflection you have seen in your structure or in the statics. The deflection of a simply supported beam is 5Q L to the power of 4 divided by 384 EI. Q is the load, L is the span, EI, E is the material modulus of elasticity of the material, and I is the moment of inertia. If you assume that these beams that we are considering are 1 foot wide, each one is 1 foot wide, and the load is transferred to them, what we have is the delta for this beam and the delta for this beam would be equal. Based on what requirement or based on what rule they are equal? Compatibility. The two deflections need to be compatible. You cannot have one deflecting more, the other one deflecting less. They are not these two deflections are not compatible. So the continuity and compatibility says that these two deflections need to be equal. Therefore, 5Q1 times B to the power of 4 divided by 384 EI is equal to 5Q2 A to the power of 4 divided by 384 EI. EI for both beams is the same because each beam is 1 foot wide. So because EI is the same, we conclude that Q1 A to the power of 4, B to the power of 4 is equal to Q2 A to the power of 4, or Q1 divided by Q2 is equal to A divided by B to the power of 4. So that means if A is 1/2 of B, A to the B, A divided by B to the power of 4 becomes 1/16. That means the load that is transferred in the longer direction is going to be 16 times smaller than the load transferred in the shorter direction. In other words, if you have 17 units of load, 16 units goes in the shorter direction, 1 unit goes in the longer direction. That's the limit. ACI says if it is that or more, we consider that one way. We ignore the load that is transferred in the longer direction because that's too small. So that's the criteria for defining one-way and two-way slabs. So why is it important? Because if you want to design the beam, you need to know the load path. You need to know which directions the load would go. If the load goes only in the shorter direction, let's say in this direction, then these beams would see the load from the slab. These beams would not see the load from the slab. Their design would be very different. Again, why? You need to pay close attention to load path. you decide you identify which direction the load goes, then you design the elements accordingly. Let me ask you this. If you did not know this and you wanted to analyze that frame, can you analyze that frame? The answer is no, because you don't know what the loads are. First, you have to identify where the loads go, then you model it and analyze it. Does everybody agree that without understanding the load paths, you would not be able to analyze those frames? One could say, let's say we don't know this, say half of the load goes in the shorter direction, half goes in the longer direction. That would be very wrong, right? Because 16 times goes in the shorter direction, 1 time goes in the longer direction. So understanding the load path and the floor system is crucially important. In fact, what I want to argue and encourage you to do when you do your capstone, one of the first things you want to design is the floor system. Because if you change the floor system, the way loads are transferred will be different. If the loads are transferred differently, all the elements should be designed differently. Sometimes I see some students who do capstone, the last week they come to me, let's say, I want to choose my floor system. My answer to them is, it's too late. Because you have to change everything that you did. Does that make sense? So the first thing you want to do is you decide what type of floor system do I want to choose. Because of 2 reasons. Reason number 1 is the load path. For instance, if I choose the joist floor system in the longer direction, which usually we do in this case, if I choose this floor system, which is very reasonable floor system, the load goes to this beam and to this beam. Because the joists are carried by shorter beams. If I choose this floor system, the load goes to this beam and to this beam. Obviously, the design of those 2 structures are very different. Therefore, if you don't know where the loads go, you would not be able to design the structure properly. That's reason number 1. The second reason is that when you want to design a structure, one of the pieces that you need is the loads. Loads include dead load and live loads. Dead loads in a structure, the primary source of dead load is the floor system. If you want to find which element is the heaviest, the answer is the floor system. So if you don't know the weight of the floor, again, your calculation could be incorrect. The weight of a joist floor system is different from the weight of a slab system. Okay, so therefore, because of these 2 reasons, you want to design the floor system first. 1, load path, that means which direction the loads go. 2, how much is the load. So because of those 2 reasons, first you decide on the floor system. And that's kind of an interesting topic when you, hopefully when you do your capstone project and you start thinking about floor system, there are lots of publications as to how you choose the floor system, which obviously is beyond this course, but that's something that you need to study when you do capstone. What is the advantage of one floor system to the other floor system? At what span do you use one floor system or the other floor system, and so on. So, however, from a design point of view, this is what we will discuss in this course. One-way floor system. Two-way floor systems is a little bit more complicated, and that is one of the topics that when I teach the graduate concrete design course, which I usually teach in the spring, like 40% of the class is related to how you design two-way slabs. So that is not covered in this course. We talk about one-way floor systems. Joist floor systems, after you learn how to design beams, designing joist floor system is very easy. So therefore, you practically can design one-way floor systems and joist floor systems. Those are two more often used floor systems. Any questions so far? Okay. Is it clear to everybody as to why most of the load goes in the shorter direction in a slab and not in the longer direction? So, let me see. Can I borrow your notebook for a moment? Because yours is kind of longer. So if you think about this as your floor system, which is a panel. What does it mean, a panel? This is a beam, this is a beam, this is a beam, this is a beam. This is really this way. We just look at it this way. So when you apply the load, the deflection here in this direction and in this direction are the same. In this direction, you imagine there is a, just think about it, a piece of wood that is 5 foot long and another piece of wood that is 10 feet long. Okay? If you stand on top of those two, which one would deflect more? The longer one. So this beam and this beam need to deflect the same amount. Which one is going to see more load to deflect the same amount? In other words, I have the 5 foot long wood and the 10 foot, so therefore more load goes in the shorter direction. Thanks. So before I continue, any questions? Anyone looked at homework problem? Last homework problem of homework set 2. So if not, I would rather really to stop here for you to give you more time, like 15 minutes till the next lecture. Look at last homework problem and see what other questions you might have. Look at them as closely as you can. You would benefit from this time instead of struggling after the class trying to figure out how to do it. Okay, so we stop here and start in 15 minutes.
I didn't hear that. I missed like some of the lecture. So you were, okay. I understand that compatibility equations. That's how we're getting this. What does
Correct.
this ratio mean?
The Q1 to Q2 is how much load is transferred in one direction to the other direction. Q1 is load transferred in one direction, Q2 is load transferred in the other direction.
So it's like,
There is some part of load goes in this direction. Let's say this is the slab and you go and stand on top of it. How much of your weight goes to this beam? How much of your weight goes to this beam? Most of your weight goes this way. This tells you how much weight in one, of course this is distributed. How much distributed load in the longer direction, how much distributed load in the shorter direction.
so this beam is
Longer. This is B, this is A, B. This was larger than 2A, not A. I'd rather to discuss this after the break so that everybody hears, because others may have the same question. Just ask me at the beginning of the next lecture.
but the thing is, I didn't hear you say that part.
Sure.
Sorry.
Yes.
But it's fine, thank you.
Okay.
So then, the